and let me start by thanking the organizers for the opportunity to speak here and also for making happen this great conference in this truly amazing location. And so I would like to speak about the results from a series of works over the years with my mentors, Andrea Cavalli, Kolya Gronov, Paul Ryan, Grisha Sizov, and Dima Volin, and also about the results of a paper with Volodya and Vitya Mishnyakov, which should appear very soon. So I was, it took me some time to decide which subject to speak about. I recently worked a bit on matrix models and two-dimensional quantum gravity, but I decided this subject would be more relevant for the conference here. So in this series of papers, we were able to realize the program of separation of variables for a large class of integrable models, so mainly integrable spin chains with the higher rank GLN symmetry. So, and we were able to resolve a number of long-standing problems in the subject, and eventually we are starting to apply the results to various observables in integrable CFTs as well. So let me start with some motivation. So the main motivation for us was to try and solve completely n=4 super-Young Mills and the dual string theory on ADS5, which is expected to be an integrable example for ADS-CFT duality. And while much progress has been made, there remains a very important open question. So for complete solution of n=4 super-Young Mills, which is the conformal field theory, we would need to know all 2-point and 3-point functions, which in principle determine all the rest of the correlators. And the exact spectrum which controls the 2-point functions is by now very well understood. Whereas the 3-point functions, the structure constants, are a much more complicated set of observables, and at the moment there is no truly satisfactory way to compute them at finite coupling or to high perturbative order and so on. So that is a key open problem in the subject. So the solution for the spectrum works by employing a variety of integrability tools. So at weak coupling, for example, single trace operators map to states of integrable spin chains, like the Heisenberg XXX spin chain. But then at finite coupling, the situation is more complicated, and one finds some novel type of integrable system, which can be, whose spectrum can be found by the method that was called here the quantum spectral curve. So this is the set universal framework of Vronsky and QQ relations, which in the end amount to realize and in the end they amount to a set of difference equations on Baxter Q functions, Q of U, with various indices, and most importantly here they should be supplemented by a set of beautiful and non-trivial analytic requirements, whereas for spin chains these functions are polynomials. Here for super-Young Mills they have non-trivial cuts whose position is determined by the coupling, and then monodromies around these cuts are constrained by some non-trivial relations. So if one manages to solve these equations, then the anomalous dimension can be retrieved from these Q functions. So this framework has been used to great effect in a wide variety of situations for many observables. So one can compute the spectrum numerically with huge precision. One can compute at finite coupling even some other observables like quark-antiquark potential. One can study the very complicated BFKL limit that has long been inaccessible. One can compute perturbatively 10 loop orders or even more. And this is just a selection of results from the large literature on the subject. But then, what can we say about 3-point functions? So for the 3-point functions, the level of control we have is much less efficient at the moment. And the idea which I am exploring is the following. This is to use the separation of variables. So in principle, for any integrable model, we expect that there should exist a special basis in which the wave functions factorize. And so like for hydrogen atom, the wave function becomes a product of components depending only on one variable, on some spherical part and radial. Then for any integrable model, there should exist a basis where the wave function is expected to become a product of Q functions, depending on the individual separated coordinates x1, x2, xn. And so then the spectral problem is naturally about the spectrum, but in quantum mechanical terms, the computation of correlation functions is in some sense about the wave functions of the theory. So if we know the simplified wave functions, then we could hope to reconstruct the correlator somehow. That's the main idea. And what's very important is that these building blocks functions should be given by the quantum spectral curve equations that I have just discussed at any coupling. And we have very good control over them. So we could reconstruct this finite coupling wave function very efficiently. So this is just a vague general idea, but it can be made quantitative, at least in some examples. So for the first time, this was done in our paper from 2018, where we considered a certain correlator, which is rather special. It's 3 local operators connected by some Wilson lines, and then in a special limit when ladder diagrams only survive. But it's still a very non-trivial observable, and we were able to show that it is given to all orders in the coupling by a very simple expression in terms of Q functions. So whereas by standard methods one gets some horrible thing coming from summation of finite graphs, here we found that it's an integral literally of 3 Q functions describing the 3 operators sitting at these cusps. And then the normalization is like normalization by norm of the state or 2-point function. So that's exactly the kind of result that one expects from the philosophy of separation of variables, and that gives hints that there should be some large simplifications and hidden structures behind 3-point functions. And, and furthermore, very recently, in the end of last year, a few papers appeared which also explored similar ideas and found related hidden structures coming from another approach for computation of 3-point functions known as the hexagon expansion. So all this gives us hope that there should be a way based on separation of variables to eventually be able to compute 3-point functions in super young Mills. And it's yes. So and then a large part of this work was done. Well, some part of this work was done during the COVID times, and so that gave us extra motivation to ensure that in social distancing and to keep all the variables well separated from each other. Yeah, so the focus of this talk will be a separation of variables for GLN spin chains. And let me see. Yeah, okay. So for super young Mills applications, we need to work with systems with a more complicated PSU 2,2/4 symmetry. But even for GLN spin chains, the separation of variables has not been barely developed beyond the simplest GL2 case. And so the 2 main questions we should ask here are the following. So first, how to factorize the wave functions. Like for hydrogen atom, they are factorized into the well-known components. So here one should find the basis where this happens. And the second question, what is the measure which appears in the scalar product? So when we go to this nice basis of separated variables, we do a change of variables that will lead to some Jacobian appearing in this scalar product, like in spherical coordinates. We find a non-trivial measure for the hydrogen atom. And then, so what is this measure for our spin chains? That's the second important question. And I will show how to answer both of them. And there is an upcoming review that I was invited to submit to, for JPZ, which hopefully should appear soon, and will describe all of this as well. So I will first discuss the construction of the basis of separated variables, and then I will discuss the next problem of finding the measure. And finally, I will speak about the extensions to field theory and the work to appear about Youngian symmetry of correlators, which is also related. So first, the construction of separated variables basis. So I will discuss in detail the example of SUN spin chains, and then I will mention various generalizations. So for SUN spin chains in fundamental representation, the full Hilbert space for L sites is that, so at each site we have a CN space, and then the full Hilbert space is the tensor product of L such spaces. And we are interested in diagonalizing the Hamiltonian, so which has this usual form, and so more precisely, we will also have some boundary terms coming from twisted boundary conditions. So, so the way to solve this model is to build a monodromy matrix based on the rational R matrix, where we introduce an auxiliary space and take a product of these R matrices. So here we will work with a deformed version of the model where we introduce generic inhomogeneities θ1 to θL at each side, and a diagonal twist as well corresponding to twisted boundary conditions. So these serve as so first they allow us to introduce extra parameters and make our model richer, but also in many cases these serve as important regulators, which in some cases can be removed later on. So then if the trace of the transfer matrix gives the commuting integrals of motion, which are diagonalized in some joint eigenbases. So how to construct the wave functions for the SU2 case? So the standard construction goes as follows. Here the monodromy matrix is 2 by 2 with its standard ABCD elements, and this B operator serves as a creation operator when we act on the vacuum with all spins are up, and then we evaluate the B operator at beta roots. So the beta roots serve as play the role of momenta of excitations that propagate along this spin chain and correspond to down spins. So they are fixed by the celebrated beta ansatz equations. Or alternatively, what will be useful for me is to think about the Baxter equation. So it's written for the Baxter Q function, which is some fixed exponent with the twist times a polynomial whose roots are beta roots. And so instead of fixing beta roots from this equation, we can fix them from the Baxter, which is a finite difference equation of second order. This plus minus are shifts. So it involves as coefficients and this fixed polynomial q theta, which encodes the inhomogeneities, and then here appears the eigenvalue of the transfer matrix, which is also a polynomial. And then if we impose that q1 and tau are polynomials, this fixes both of them. We find a discrete set of solutions. Which,
why are there so many pluses and minuses?
Because it's shift, so here it's shift by I, here it's shift by I over 2 in the opposite direction. So that's it. There's nothing I can do about that. So it's a second order difference equation. You have q of u plus I, q of u minus I, and q of u.
Why it is 2 plus?
Because here it's shift by I, but this guy is shift by I over 2. So 2 twice by I over 2 makes so yeah, so this is the notation that I will use a lot to yeah, so then how does separation of variables work here? So the thing is that the idea is the following. So with this construction of the eigenstates, let's consider the eigenbasis of this B operator. So it is a polynomial of degree L, and we can make explicit its roots as operators. They commute with each other. And we can diagonalize them simultaneously and label the basis by their eigenvalues. So then what happens is that this is the basis in which wave functions will factorize. This is the basis of separated coordinates. And one can see this immediately from this construction of the wave function. So if we consider the scalar product of x with psi, so then each b is a product of u minus x, and here are many u's, so we get a product of all u's minus all x's. The x's are diagonalized on this basis. And this thing is nothing but the q function evaluated at x. So what we find is the product of q functions, each of them is evaluated at its own value of the separated coordinates. So that's exactly the picture I showed. In the beginning, we have factorized our wave function into a product of q's. So one subtlety here is that since B is a creation operator, naturally it cannot really be diagonalized, but instead, if one does an extra similarity transformation in the auxiliary space on the monodromy matrix, so then the new B operator will be a linear combination of the previous ABCD, and this operator we called B good. So it turns out that non-trivially it retains all the nice properties, it still creates the states. And that's a rather non-trivial fact already in SU2 that was proven in various ways in various papers. But then, since it's now a mixture of all ABCD, it can be diagonalized, and we can actually find its spectrum, and all works literally like I said. Then one can ask what are actually the values that these separated coordinates take. So it turns out that each of them can be assigned to an inhomogeneity, and then it takes the values in homogeneity plus minus I over 2. And so in possible combinations of signs give 2 to the L options. So this basis contains 2 to the L states, and which means indeed it's a basis of the Hilbert space of this dimension. So that's what we call the SOV basis. So this was all worked out by Sklyanin back in the beginning of 90s. But then for the SU3 case, the results in the literature were much more, were much less available. So in the paper of Sklyanin, the B operator was proposed. It is now a trilinear polynomial in the monodromy matrix elements, and it's written in terms of its quantum minors, which are subdeterminants with extra shifts. But what we realized in our paper is that this operator can be used to create the states just like in SU3. So it was proposed and it was suggested that it should separate variables, but remarkably it can also be used to create the states just by acting on the vacuum and repeatedly and evaluating it at the beta roots. So that's a surprisingly simple construction, which is very compact, and it was unknown despite the huge literature existing on the subject. So this construction, for example, is much simpler than the usual nested beta ansatz because it involves a recursion. So one should first solve an auxiliary spin chain, SU2, and then construct the wave function of SU3 spin chain as a set of exponentially many terms, exponentially many in the number of excitations. Whereas here we have just linear complexity in number of excitations. We just act with BBB like in SU2. So it's a rather surprisingly compact construction. That was also hard to prove rigorously. We did it in some special cases in our paper, and then I will show a couple of papers that really proved it completely. But the upshot for us is that what's very nice is that factorization of the states follows from this construction immediately, just like it did for SU2. If we contract this eigenbasis of B with psi, then we find the product of Q functions. And the wave function becomes factorial.
And what is this GOOT stays for?
Good. The word good. It's a product by concatenation.
Like the original. So the thing is that if you just take literally this operator, then you cannot diagonalize it, and also it's mainly consists of just 0 entries. But then we do this extra transformation in auxiliary space, and then we acquire the new operator that we call the reason for the name. I hope it will. It's very good.
It's not good, it's big.
Yeah, it also contains, kind of a moral message, but that's not.
So is there? What do the beta equations look like with this B good? Are they also nested?
Yeah, the beta equations are the standard ones. So yes.
But you have a twist, right?
They are nested. So what one should do is to solve the beta equations for both. These are momentum carrying roots, and there are also auxiliary roots. So one considers the solutions of the beta equation, then one just drops the auxiliary roots from that and plugs in only the main roots. So they secretly depend also on the auxiliary and on the other.
Also in the
remaining equation.
And was your twist only diagonal, or was it?
The twist is diagonal here, but well, after this transformation, there is no really distinguishing between diagonal and non-diagonal. They are all mostly on the same footing. So just I finish this. And so another way to think is the following. One can just consider the Baxter equation, which is a third-order difference equation in this case. And it is for the polynomial whose roots are precisely these roots. And then if you demand that all 3 solutions are polynomials, it fixes them. So it just fixes them, and you never need to invoke auxiliary roots at all. Okay, so
You answered my question.
Okay. It's nice. Yeah, right. So this was the SU3 case, but then all of this extends to SUN case as well. So for the SUN case, the B operator was proposed first by Fedor Smirnov, and then in another paper, and then we also rediscovered it, and presumably the same operator, and wrote it in a more explicit form. So the statement again is that for any SUN you can create the states just by BBB acting on the vacuum, so which is quite remarkable, since in SUN by standard methods you would need to go through many n-1 recursion steps where you solve many auxiliary spin chains, and only then you recover the actual wave function in the nested beta ansatz. So, and we can here also find the spectrum of X operators like before. And yeah, so this construction is highly non-trivial, and it was proven rigorously in a series of papers. So first for SU3 by in a very involved and heroic paper of Andrei Lyashik and Slavnov. And then the full proof for SUN was obtained by Ryan and Volin by some invoking various representation theory arguments. And they also showed equivalence with another way to build the eigenbasis, which was proposed later on, so in a series of papers by Maillet and Nicoli. So, and that's a very different point of view on the problem, which is also useful in many situations. So there, one builds, instead of diagonalizing B, one builds these states by acting on some reference state with transfer matrices evaluated at special values of the argument. But the and so these two constructions turn out to give the same basis. So, and let me also mention that for super case, this program has been realized only for SU1/2 in my paper with Kolle, and the general case remains an open problem. So now let me come to the next part, which is now that we have learned to factorize the wave functions, we should learn how to compute their scalar products in the SOV basis. And so that is the problem known as computing the SOV measure. I think there was, so the structure is the following. So at least what we know from GL2 type models is that the scalar product of wave functions in separate variables takes the form of an integral or sum over their values. And then one wave function is represented by a product of its Q functions, the second one by its own Q functions, and then there is some non-trivial Jacobian or measure, which at least in the known cases takes the form of a kind of double van der Monde product of the separated variables and their exponents of this kind for two models. And then, but for higher rank GLN models, there have been simply no results in the literature on this.
Sorry, but I thought the X variables were like discrete eigenstates that you operate, but here you take them continuous?
Yeah, so for discrete case, like I said, you would have a sum instead of integral. For say SU2, it would be the sum over all values of separate variables, and then you evaluate this expression.
Okay, but here it's just...
Yeah, here I write integral for non-compact case. You can write it either as sum or as integral. So, and this in the following also I will mean by this integral, in some cases it's actually a sum. You can always write it as an integral, but then in some cases you can reduce it to a finite sum by evaluating on residues and such tricks.
This is an off-shell formula, or?
So strictly speaking, this is on-shell, but in some cases, but if you define your wave function as something that overlaps with X as product of Q's, you can make it off-shell as well. You can define off-shell functions in many ways, but one definition is the following: just take any function Q and require that your function overlapping with X is the product of Q of X, where Q does not necessarily satisfy Baxter. So that is a very useful also definition of off-shell, and then the scalar product will be this.
Can I ask a silly question? Wouldn't that be zero if psi is not different from psi?
Yeah, exactly. So if it's actually on-shell, it will be zero, or like zero or norm of the state. Yeah, but so there, it is still very useful because it gives the general structure, and then you can define the off-shell version, which will actually be non-trivial. And then, but then what happens is that you can also translate various operators and into this basis, and then if you insert it here, it will result in some minimal modification with some extra insertion in this formula. So this formula is that even though it's actually 0 or 1, it is a very useful starting point in all situations. Okay. So for higher rank, this measure has not been known at all in the literature. So I should mention there was a paper of Smirnov-Tsetin where it was found in the classical limit, but apart from that, it was not known.
So the integral of all possible values of beta roots?
No, not of beta roots, but of separated variables, which are the, like I said, eigenstates of B operator. So this is very different from beta roots. They are, for SU2, they are just inhomogeneities plus minus I over 2. Okay? So you sum over these values. Why is this measure useful? Just to say again, so to compute some correlators between wave functions, one inserts between them the complete basis in this form, where x is this base in which wave functions factorize, and so they reduce to Q functions, but the price to pay is there is a non-trivial measure, which is the inverse matrix of overlaps of these states. But so then one runs into a problem which perhaps is the problem that has prevented solution computation of this measure for a long time, because if one looks at the basis that I showed before for SU3, then overlaps between these states look really complicated, and it's hard to find some structure in them. But what we were able to find a way around this, and the idea is that the idea is to separate the Bra and Ket wave functions in two different bases. And then it turns out that one can find a basis in which the measure becomes simple and nicely computed. So let me show a shortcut to deriving the correct answer, which we used and were able to find the result in an efficient way. So the idea to find the measure is to start so like already was discussed, if we have orthogonality, different transfer matrix eigenstates are orthogonal, but since in separate variables they become Q functions, we must have some kind of orthogonality property for Q functions. And this orthogonality property has to follow from the Baxter equation, since it determines Q functions uniquely. So there should be some structure in this Baxter equation. And we observed that, and probably for SU2 this was part of some known folklore, that the Baxter equation can be written in terms of a self-adjoint operator. So if we rewrite the left-hand side of the Baxter equation as this shift operator, so here is shift in one direction, in the opposite, and here is no shift, and this Q theta, I remind you, is a fixed polynomial. So acting on Q function, this is the operator that annihilates it, that's the Baxter equation. But what's remarkable is that this operator is self-adjoint with respect to a very simple scalar product, or bracket. So in this case, this bracket is just an integral around the large circle of your function. This integral can, in practice, be evaluated by poles, since it will sit on these residues coming from here. But we observe this nice property, and it comes from some symmetries in the coefficients of the Baxter. And when we have a self-adjointness property, then like in quantum mechanics, we can immediately translate it easily into some orthogonality statements. So to be more precise, we can introduce, first of all, not one, but L such brackets, where we insert periodic functions, exponents, which for Baxter equations are like constant, because it's a difference equation. And then, so the Baxter, this operator depends on the states only through the transfer matrix eigenvalue. So this transfer matrix eigenvalue contains integrals of motion, which in the twisted situation uniquely identify the state. And then, like in quantum mechanics, we start by considering this combination, where we have two states, A and B, and we consider the difference of these two operators. So this difference comes only from the difference of transfer matrices. But at the same time, so this object is zero, because we connect with OA to the right, and it annihilates this Q function, and OB, by self-adjointness, we connect to the left. So the result is zero, and since the difference comes from transfer matrices, we'll find some linear relation on the differences of integrals of motion of the two states, where the coefficients are some integrals constructed out of Q functions.
So the Baxter equation has two solutions.
Yeah, so here we choose the one which is
yes. How you choose?
So in principle, you can choose any solution, as it turns out.
No, you can't choose. If you take the linear difference equation, the solution is the linear combination of two independent solutions.
Yeah, so here in the twisted situation, we can distinguish two solutions by their twist, by this exponent in front of them. So that's what we do. One should, for the first state, we take the solution with one fixed exponent, for the other state, well, with the same exponent. In fact, you can use the second Q function as well, and the argument will be almost the same, but I will not go into this. Then for more complicated situations, like non-compact representations, one has to choose the polynomial Q function here. So what the result is that we find a linear system. Since we had many brackets, in fact L independent brackets, we find the L equations for these L differences of integrals of motion. But then, since for the twisted case, the integrals of motion uniquely identify the state, if we have two different states, then at least one set of integrals has to differ. So this linear system needs to have a non-trivial solution for these differences, and that means that its determinant has to vanish. So we arrive at this relation, this determinant of combinations of integrals of Q functions. It must vanish whenever we consider two different states. And so that's exactly the property of a scalar product in separate variables.
Yeah, sorry. So I know just like say in the alternating six-vertex model, right? Hamiltonian is not Hermitian, for instance, right?
Alternating six. What do you mean by
Well, I
alternating?
mean, if you have arbitrary homogeneities,
Yeah.
the Hamiltonian won't be Hermitian.
Yeah, it doesn't matter.
So this
So the orthogonality, which I mean here, is the zero scalar product between left and right eigenstates. This does not depend on any reality or hermeticity or anything. Just for any operator, if you can diagonalize it, construct set of right eigenstates, you can also construct set of left eigenstates, and there is a natural pairing between them, which such that they will be orthogonal. So it's just a space and a dual space, if you wish.
So I know for sure that this scalar product is not scalar product is not the usual scalar product on a chain where, say, for instance.
Yeah, if you want to insist on some reality property, then it will not be friendly to this reality.
And it's not positive definite either, right? It wouldn't be
Yeah, it's
in
not
general.
necessarily positive definite, but it's the most natural scalar product where you just have your transfer matrix, you have its eigenstates, and you have left eigenstates, and there is a natural pairing, they will be orthogonal. You don't need to complex conjugate anything or do anything like that. It's just left and right eigenstates, vectors and covectors.
I know that's
Yeah, well, so what happens is we find this determinant has precisely the property of scalar product of two wave functions. So it's a natural candidate for the actual scalar product in separate variables, and indeed, we observe that it is precisely in agreement with known results for the scalar product in SU2. So that's a shorthand to deriving it without going through without going through the construction of separated bases, without calculating the measure explicitly, and so on. So that's a fast way to get the answer. And so what's very important is that this generalizes almost immediately beyond the SU2 case. And while for SU2 it was more or less known, perhaps for higher rank it certainly was not. So how it works for SU3, this is what we worked out. So now we have several changes here. So first of all, we have different types of beta roots, and in addition to the Q function with momentum carrying beta roots, we also have auxiliary roots, and they will play an important role now here. So in this case, they are encoded in Q functions with the upper index in some standard notation. And so we have, in fact, several Q functions of this type and of this type, corresponding to duality transformations in beta and that, so choosing some path on the Hasse diagram. So the main new feature is that these Q functions should also appear in the scalar product in order to get a simple measure. So what happens is that now we have a Baxter equation for the Q functions with a lower index and another Baxter equation for the Q functions with upper index. So they involve its coefficients, again, the transfer matrices, now there are two of them. And whereas for SU2 this equation was just self-adjoint, now we find that these two equations are conjugate to each other, in the sense, again, of the same bracket, just an integral. So with this remarkable property, we can now again run all the same logic. We consider the difference of two operators for two different states and so on. And then, so the same argument leads to orthogonality, so leads to a linear system for the differences of integrals of motions of two states with the coefficients constructed out of Q functions. Now here we have some freedom in which Q functions we choose, so basically all the choices are good. And in the end, we find this linear system for two L variables, these differences, and two choices. Well, and we have two L equations for them in the end. So that's a complete linear system, and again, we have to require that its determinant vanishes. And so we arrive to the scalar product in this form. So now one of the states is characterized by its Q function Q1, but then the other one is characterized by the set of two Q functions with upper index, in this case Q2, Q3, and also they appear with some shifts in this determinant, but the scalar product is again a determinant. So then each bracket can be evaluated by residues, and it's the sum of residues at values related to inhomogeneities. And so if we expand it, then we find the scalar product has this form. So this block contains the first Q function, and what's nice, the values at which it is evaluated matches the spectrum of the B operator that I showed originally. So the separated variables are actually what appears here. And then for the second Q function, we have something more complicated. It's not just Q individually, it's some combination of two Qs. So that's its representation in separated variables we expect. So the natural question to ask is there actually a basis in which this is also the components of the factorized Q function for the other state? So, and the answer is positive, and we were able to understand this.
Sorry, Phil, can I ask? Can you go back one slide? I mean, maybe this is stupid, but so here you use the argument here that the i's, the integrals of motion, then
Yes.
Each state, they identify state, right?
Yes.
We have global symmetry, right? That's not true.
Right. So here we have a generic twist, and with the twist, it's true.
Okay, I see.
Yes.
Thank
So
you.
then if removing the twist is a subtle matter, and that requires further work. Yeah, so what? So now we would like to find the basis. These are the wave functions of the second state, and we can do this. So we find that the cat and Browell wave functions are factorized in two different bases. So the first wave function is factorized in the usual X basis, which are the eigenstates of Sklyanin's B operator, but the second one is factorized in the base of eigenstates of another operator, which we found. So it looks much like the Sklyanin one, but it's kind of a dual operator, and the shifts here are a bit different. But it serves to factorize the other wave functions. And then now we can compute it for some explicit examples. For instance, the actual measure of the scalar product by evaluating the inverse matrix to overlaps of these two bases, which is what we have to do if we insert the resolution of identity. And so this thing we can compare with what we found, with what we find from this determined result. If we just expand it and collect the efficiency of Q functions, we find some coefficient, which is the measure. And remarkably, it precisely matches the overlaps of these basis elements, so this puts the construction on a firm ground. And so it means that this actually is the scalar product of two wave functions in separated variables with the control.
Could you specify which representation SU3 you're talking about?
In this case for fundamental, but I will say in a moment how it works for more general.
Fundamental meaning lowest
Three-dimensional.
Dimensional one.
Three-dimensional, yeah. But I will show later how it works for even infinite dimensional as well. So a couple of observations, so this I will skip. So then there is an alternative approach to computing the measure that was proposed by Maillet, Nicoli, Vignoli in 2020. So they fixed the measure in a very different way. They derived recursion relations for individual components of this matrix Mx, Y. So they look rather complicated and fill up more or less a whole page, but the result presumably should be the same as what we find from this determinant. That would be interesting to prove rigorously. But one advantage of our presentation is that the scalar product immediately has the form of determinant, and so it should be useful for a variety of applications, hopefully. So to answer Grisha's question, so what we managed to do in a further paper is to compute the measure for any SUN explicitly and for any spin. So we consider representation, highest weight representation with the weight of this kind S, and the rest is zeros, and S can be in principle any complex number. So that includes in particular infinite dimensional representations. And we were able to find the matrix elements of the measure explicitly in the form of some sum over permutations and some van der Monde determinants and so on. So one can plot which, these elements for some fixed length. Most entries are zero, but then there is some nice non-trivial structure. So now we understand this measure very well. So and one last comment is that one can compare this measure to the discussion in the paper of Smirnov and Tsaitlin. So one can rewrite it as some state-independent operator which contains also shifts of the spectral parameter. And then in this form, it is very similar to what they conjectured based on semi-classics and quantization of algebraic curves. So this shift operator naturally becomes one of the variables in the spectral curve, and the result looks quite similar.
Can you clarify what's the goal? To just write explicitly
No,
the
goal-
matrix
yeah.
elements, or
No, the goal is to compute correlators. So to actually, so this is just a skeleton. We would like to insert here some operator, translate it to X basis as well, and then this its form factors hopefully become very simple, just U, Q, and so. And I will show such examples in a moment. The goal, so that's the goal, to compute various soft-shell observables. Okay, this I will skip in view of time. So how can we actually compute some correlators? So the first example is the following. So what we can nicely compute, again using quantum mechanical logic from perturbation theory, are form factors of derivatives of integrals of motion in some parameter like twist or inhomogeneity. So by using some again the self-adjointness property and what's known in quantum mechanics as the Hellman-Feynman theorem, so one can find for them again a linear system which has some solution in terms of a ratio of determinants. So I said that these are not diagonalized on the usual eigenstates of transfer matrix, they are derivatives of integrals of motion. But nevertheless, one can rewrite them in a nice determinant form, and what appears in the denominator is the norm of the state coming from the scalar product that I showed before, which is also very natural. And then, for example, if we take a derivative in a fixed inhomogeneity, this gets local operators acting on a particular side of the spin chain, which is also nice. But then there is a much larger class of operators which are also under control. So for example, one can compute overlaps of states with two different twists, which diagonalize two different Hamiltonians. And the result turns out to be, again, a determinant of the same kind that I showed. And furthermore, one can construct various off-shell wave functions. For example, by acting on the reference state with B operator, evaluated at arbitrary values, not necessarily beta roots. So and then, with the C operator, one can do the same. And the scalar products of all these states with each other, again, will be determinants of the kind that I showed before. So because B and C are friendly to separation of variables. So this provides a huge set of states whose overlaps we can compute in a nice determinant form. So and this B and C operators are rather non-trivial. So and in combination, this likely gives a complete set of operators for our spin chain. So in principle, one should be able to reconstruct any operator from these ones which are under control. So then in practice, we are looking for further tricks, and we are still thinking what's the most efficient way to express the result. So then one example is recently, so based on what I was said, further simplifications were found in this paper by Gromov, Primi, and Ryan, and they found a set of operators which have particularly simple correlators. So all of their matrix elements can be found in determinant form like I showed before. So I will not go into details how these operators are constructed, but they form a complete set, and some of them are very simple. They are just individual matrix elements, matrix entries of the monodromy matrix. So for SU2, for instance, these are operators T12, T11, and T21. And for SUN, there would be like something like n relatively simple operators, and some of them are more complicated, and so on. So this should be, this picture uses that the SOV basis, in fact, is independent of twist. And due to its simplicity, it should find hopefully many applications, including efficient theory, which we are thinking about very actively. Okay, so this, so now this, like I said already, this construction generalizes more or less directly to non-compact representations, but in view of time, I skip all of this. So let me speak finally about some extensions to field theory, which is our eventual goal in this whole program. So having understood the spin chains.
Sorry, so you finished that part?
Yes.
Can you possibly focus on one correlation functions which you computed? So doesn't matter how you computed, but what did you compute?
Yeah, so like, well, let's see.
Just one out of many.
Yeah. So I'm trying to go back, but it's not so easy.
Should I go backwards? Yeah.
Yeah, more. Let's go. More. Yes. A bit more. Yeah, here, next. Yeah. Okay, so next, let me try. Okay, wait. Let me try to.
We can change the battery.
Well, that would be nice. Maybe you can press a bit more.
Just say stop.
You are going in the wrong direction. Let's go in the other direction. Stop. So, if you consider the B operator and arbitrary values of the parameters, and C operator also. So take any number of these operators sandwiched between two eigenstates. So this is a rather non-trivial object which we can compute immediately in determinant form. That's one example. So then, like I said, individual.
Just listen. It will be a function of V1, V2, Vk, all this. So it will be pretty sizable function, right? Of many variables. How does it look? In what form?
Well, it's a determinant. So it's a determinant of.
And it's off shell.
Of this kind. So 2L by 2L determinant. So here the Q functions, they will be a product of U minus all the values of these parameters. That's how they will look like. And then there will be some insertions, like not just this power of U, but there will be some other stuff, like some fixed polynomial or something, coming from these B and C operators. So that's the kind of determinant I mean. And each bracket is an integral over a big circle, or if you wish, it's a sum of residues. And the same representation exists for less esoteric objects than B or C operator. It exists for some individual elements of the monodromy matrix, like for SU2 for these three elements, for SUN for like n-1 elements. So for off-diagonal form factors of some monodromy matrix elements immediately writable as determinant.
You get L-dimensional integral.
Yeah, so the...
Is it easy to get some explicit, when L is large,
Yeah, so that's one of the things which we are thinking about. It's a very natural application. Look at some thermodynamic limit and so on. But this should repeat the story known as in SU2.
What about Karepin, McCoy for SL2, the determinant expression?
Yeah, it would be nice to try and generalize it here. So that's an interesting problem to look at. So our determinant is of size L. So like Karepin determinant also roughly of size L. So it's related objects. Okay, so in view of time, maybe let me just say a few words about what I wanted to finish on, and then we can discuss a bit. So what can we say about first applications to field theory? So eventually our goal is super young Mills, but so to start with, we already found some simplified examples in super young Mills where we find correlators in very simple form through Q functions. But then our testing ground is going to be probably the fishnet theory, which already appeared in several talks here. So this is the theory of two interacting scalars where integrability is visible directly at the level of Feynman graphs, and then the whole machinery can be translated to here. And in particular, so we already were able to find the, so we cannot yet realize the separation of variables rigorously here, but was for some examples like correlator of two operators and Lagrangian, we find very similar structures to spin chains. Again, we find the result in the form of ratio of integrals of Q functions. So this, to be more precise, so here we find SO4, 2 spin chain in principal series representation, and the correlators in this spin chain are, so wave functions of the spin chain are some particular correlators in fishnet theory. And then by invoking the various tricks we learned from spin chains, we can compute already some non-trivial correlators here, for example, from derivatives of integrals of motion. We find two-point function given by this kind of Feynman diagrams with the insertion of some local operators acting in a particular place of the diagram, and we can compute these two loops. And like I said, we are learning more about spin chains, so we hope to extend this to many more examples. So finally, let me, so this I skip. So in n=4 supreme Mills, we have in fact the starting point. We have this orthogonality relation coming from the quantum spectral curve, but So hopefully this should also allow us to compute various things, but the main difference is now we have infinitely many degrees of freedom. We should try and identify good ways of integrals of motion. So then finally, just a couple of words about the work which should hopefully soon appear with Kazakov and Maslyuk. That's about slightly different subject, the Youngian symmetry relators. So here we consider the most general fishnet CFT, this Lump CFT. And so where we start from a Baxter lattice of some set of intersecting lines, and we find, and the propagators are given by, are determined by the angles in this lattice, and it's defined in any dimension. So this gives a set of Feynman graphs that should be integrable in any dimension. And what we were able to find is that, in fact, these graphs have a Youngian symmetry. So for a Feynman graph with an external legs, one can define a monodromy matrix built out of conformal Lax operators, so which acts on the these external legs of the graph, and the graph as a whole, this graph as a Feynman integral turns out to be its eigenstate. So that's a very powerful statement, which in particular leads to some differential equations for these Feynman integrals. So this was worked out originally for the original fishnet theory in this paper from 2017, but we were able to generalize it now to any conformal dimensions, any graph geometry, and any even dimension of space-time. So the main new idea is that we draw this monodromy matrix as a we find these Lax operators are naturally associated not to the faces in which the vertices sit, but to the dual faces. So we construct this contour around the diagram, and then by various moves we can shrink it to a point. So can you go to the previous? Yeah, now the next. No, in the forward direction. Yeah, one more, and one more. Yeah, so the parameters of these Lax matrices are determined from the geometry of the graph, from these local angles. So we hope we get new differential equations for these integrals in any dimension. So this Youngian invariance in 4 dimensions has already led to various powerful results for correlators and amplitudes. Some cases can fix them completely. So, and it would be very interesting to explore the relations between this Youngian symmetry and separation of variables, for example, for 2-dimensional examples that are linked with Calabi-Yau geometry. And we also hope to bootstrap new integrals in this way. Okay, so I come to the conclusions. So there are many open problems, and hopefully this, now that we understand how to separate variables and spin chains, this should lead to many applications for higher rank spin chains. So one mathematical question I'd like to ask is, what is the algebraic meaning of this integral of 3Q functions that we find? That should involve some new insights from representation theory and may open some deeper subjects in the end, or be related to it. Okay, so in view of time, I just leave it here, and thank you for your attention.
Just not rather a comment than a question. So I want to explain. It's briefly what is the meaning of this measure. So suppose you quantize in action and variables, yes? So which is a kind of wrong, but so in the first estimation is correct. The measure will be just a wedge product of angles. But you know that correct quantization is from separated variables. And the separated variables are related to angles by Albert transformation. So you undo Albert transformation, right? And you obtain some Jacobi determinant. And this is the measure. So this is classically, but so it almost does not change for the quantum case. So this is the origin of this measure. It was, by the way, written not only in, I think, classical case was also considered by Dubrovin.
So for the classical, so you say Dubrovin had the measure for the quantum case in some form?
For classical case.
For classical, yeah, for classical, yeah. So yeah, I should also cite him probably in addition to your paper.
Cristiano, maybe. I can go after him.
Hello. So I'm new here. I'm sorry I came so late for the workshop. So my name is Matthias Christandl. I'm working in quantum information. which is really only slightly touching on the subject. So we've been using methods from integrability to construct spin chains where the couplings are varying, so where they're not the same, but where we want specific properties for spin chains that are used for quantum wires. But we've of course only used spin chains with two-dimensional systems. So can you use these methods now to do this inverse? Okay, so to now construct spin chains that have certain properties.
Well, so in this form, I'm not sure we can say much. What I can say is that, so here we consider spin chains with nearest neighbor interactions. So you would like to imagine more complicated models with varying interactions or something like that?
No, I want also nearest neighbor interactions, but non-uniform.
Yeah, I see. So this I'm not sure how to do immediately. With this inhomogeneities, we already have some non-uniformity in principle, but probably it's not enough. But I mean, one step in this direction, we are thinking about applications to some longer range spin chains, where again you would be able to take various limits and get new models. So this was discussed to some extent in Jules' talk. Maybe we could continue discussing later.
I just wanted to say that with respect to like applications, like studying scale limits and so on, if you want to study scale limits of norms and operators, like the type of scalar product that you impose on the lattice is extremely crucial. And there's actually an infinite number of scalar products that you could impose that satisfy this orthogonality condition for the Gödel states.
Yeah, okay.
So, it would be like in your presentation, it's sort of implicit, sort of there, and it would be good to explicitly understand what that scalar product is, whether you can change it, for instance, by value of formalism and so on.
Yeah. I see. But for SU2 case, it was more or less worked out, and all these integral representations, they do correspond to, I imagine, the actual interest.
Well, there's a definite one. With no fact in between.
Yeah, I think it's,
No, it's inhomogeneous.
Yeah, in the homogeneous. So in homogeneous, that's a different story.
So for me, the first test of, say, usefulness of the thing would be to calculate one-point functions in the thermodynamic limit, right? Because then you can compare with known results. One-point functions.
Yes.
Can you already do that?
Yeah. Well, not yet, but that's one of the key problems to study the thermodynamic limit. And as I understand, the explicit knowledge of the measure is useful there. There was some discussion in a recent paper of Kitanin and co-authors, and now we actually have the explicit expression for any matrix element of the measures. Hopefully, this should help to study this.
But you have expressions for the one-point functions in the inhomogeneous case?
For finite length, we have this large set of correlators that I showed in the, for example, diagonal matrix. Any off-diagonal matrix elements of some elements of monodromy matrix, they are easily computable. Probably that's what you mean by one-point function. And by this inverse scattering method, you can reconstruct from them, I guess, individual spin operators.
Probably by taking derivative with you.
Yeah, the over derivative, yeah. So by some, so in the end one would need to evaluate some kind of functions in this thermodynamic limit. So that was studied extensively in SU2, led to some rich mathematics.
Even not,
I think maybe it is, maybe last question from
It's a very general question, but at the very beginning, so you talked about the separated variables for the hydrogen atom wave function. But in this case, so okay, you have separated variables, but you have different variables and also different functions.
Yeah.
So here in all your spin chains, you have same function and same variables.
Yeah,
Do you do something specific about integrable spin chains which separated variables like this? I mean, is there?
I don't know the answer to this question. Could there be some integrable models where they don't factorize into the same Q functions?
Yeah, same
Probably.
different variables.
I have not seen such examples in literature. Maybe they exist. That's a very nice question.
It's something in structure of spin chains.
Well, here it all has to do essentially with Youngian representation, so it is, in a way, it is quite rigid in the end.
Strictly speaking, you give an answer for separated variables, but you don't give this transformation.
Yeah, that's we don't construct explicitly. Yeah, that's.
There's some questions which you cannot open, about completeness, for example.
Well, about completeness, we can say something that, like I said, there is a set of operators which is proven to be complete, and whose form factors can be calculated in this determined form.
Which you're dealing with infinite dimensional representation. Not the one which
For infinite dimensional, I'm not speaking about that. That was for fun. Yeah, but to prove completeness, of course, that would be complicated.
transformation.
Yeah, that's an important open problem. Yeah.
Okay,
Yeah, I think maybe it's enough.
it's not your business.
I can go on, but I think we all want to.
Will you show the element?
The question is very hard to answer.
What is P?
P is d by dx, and x here is a 4 component, x1, 2, 3, 4. P is also d by dx 1, 2, 3, 4, and they are multiplied by some sigma matrices.
Sigma man.
Yeah, sigma. So this is a 4 by 4 matrix split into 2 by 2 blocks. It's the spinor representation of SO4, 2, so with 4-dimensional auxiliary space and realized by sigma matrices.
So, and what's the relation to Fishman?
This is the Fishnet-Feynman integral of the kind that I showed. They are invariant in direction. They are eigenspace of the monodromy matrix built from the theory.
Okay, so let's thank the speaker again.